I'll begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students again, and just pray you help us use this time wisely, Lord, just to understand a little bit more about extension fields and how they work, Lord. In your name I pray. Amen. Okay, so I think most of today I'm talking about, let's see here. I'm trying to remember where we got to. I think we got to Corollary 13, right? Then the next example, what's he do here? He's looking at, this is quadratic extensions over fields not of characteristic 2. And the takeaway from this example is that an extension of k over f is degree 2 is of the form f adjoining the square root of d, where d is an element of f which is not a square in f. And conversely, every such extension is an extension of degree 2. For this reason, extensions of degree 2 of f are called quadratic extensions of f. So they're results. If we have, so what would the square root of d be defined to be? What does square root of d mean? If we call that, let's say x, what's that mean? X squared is equal to d, right? Now, in our usual context, we also impose that x be positive, right? But this usage of square root is a little bit more general than that, right? Because here f doesn't have to be a real field. But the point is, if we have, as he said, a field of characteristic not equal to 2, and you have an extension, k over f, right? Stink. With our notation, k over f equals to 2, right? Then there exists square root of d in k with the square root of d not an element of f, all right? Such that what? K is equal to f adjoin the square root of d. We have seen lots of examples of this already, right? I mean, q adjoin the square root of 2, q adjoin the square root of 3, these sorts of things. All right. Theorem. I guess I'll put it over here. Theorem 14, really the main event for today. Let f be a subfield of k, be a subfield of L. So in other words, L is an extension over k, and k is an extension over f, all right? Then the index, the degree, got to get that index out of my brain. So the dimension of L as a vector space over f, okay, that means, is equal to the product of the dimension of L as a vector space over k with the dimension of k as a vector space over f. As he says, the extension degrees are multiplicative. Also, if one side is infinite, the other side's infinite. So let me add his little picture. It's probably helpful. So we've got f K, L, and he says, so basically here you have what? You've got, you can think about this being that degree, and this right here being this degree. I can't do math. L, duh. And then in total, right, we have L over F, and there's just the product of those two. The other way to draw this picture, though, that's probably useful is that it's L, K, F, all right? And let me just introduce some notation. If the degree of K over F is, oh, let me be careful not to. He uses M and N in a specific way. Let me not be so unfortunate as to use them in exactly the opposite way. So L over K he calls M, as in mummy. K over F he calls N as in nenu nenu. There we go. So if you have this tower of fields, sometimes we put numbers on the lines connecting the field and the subfield, and those indicate the dimension of the extension over the base as a vector space. So like, I'd put an M here, and I'd put an N here like that. Okay? So the proof is actually very simple. And just really a calculation, more or less. So what does it mean? So we suppose, that I'm going to do the finite case, okay? Suppose the L over K, as I just said, is equal to M, and K over F is equal to N. And that means that there's a basis, right? So there has to be a basis. So he uses the notation. I'll stick with his notation as to not introduce yet another set of notations. But so L over K, he uses alpha 1, alpha 2, dot, 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 alpha M, basis. Right. And for these, he'll use beta 1, beta 2, dot, 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 beta N as a basis. Now, since we're dealing with two fields, right, let me be clear. So the alpha basis covers all of L via K linear spans. So we take linear combinations with coefficients from the field K. That gets us every point in L by assumption. On the other hand, the beta basis covers what? All of K via what kind of spans? Via F linear spans. Right? And we also have the assumption that the alpha basis is linearly independent with respect to what? With respect to the field K. Whereas the beta basis is linearly independent with respect to F. Right? Okay. So consider, what should we consider? Well, what we're going to do is think about an element of L. Let's let Z be an element of L. Right? Well, then that's, equal to the, if you'll allow me, I'm going to call that the span of alpha. And to be more specific, it's the span sub K of alpha, right? Which means what? there exist constants, you know, let's say C1, C2, C how many? CM, yeah. These are in where? K, right? Such that Z is equal to the sum. I equals 1 to M of C sub I alpha I. But C sub, let's say C sub j, right? Or maybe I should say C sub I. Yeah, I probably should say C sub I. I'm going to save that j for a different sum. What was that? No. It's clippy clips. Oh. I think I need to push the test back a week from where it is in here. I was going to tell you guys earlier, because I should collect that homework. I should give you guys a chance to absorb the solutions and like collect your thoughts about what just happened, and then give you the test. It's not friendly for me to collect the homework and then 2 days later just give you a test. There's no need for that in here, right? You guys are not going to be like, oh, I'm so confused. I'm going to do everything in Galois theory on the field extension test if I cover like a lecture of Galois theory before the test. It doesn't matter to you guys to have the test pushed back a week into lecture material past the test. You prefer that, in fact, right? You're logical people. More time for material to sink in is a good thing. So that's, whenever the test was scheduled, I was planning to push it a week back. I meant to tell you guys that earlier, but there's been so much excitement this week, I forgot. Not for you, but for me, you know. I mean, this week has been boring for you. Let's see your CI. But CI is an element of what? Well, it's an element of K, right? Which is equal to the span sub F of the beta basis, right? So that implies that there exist, and in fact, by the way, let's be a little bit greedier. There exist unique, let's say, A sub I j in F, such that, you know, C sub I is equal to the sum j equals 1 to n of A sub ij, what? Beta sub j. Uniqueness comes from the fact that they're bases, right? I mean, we proved that that's essentially the fact that the coordinate vector is well defined, right? There's a unique set of coefficients which gives a particular vector for a basis. That uniqueness comes from linear independence of the basis. We know this from linear. It's still true here. Now, you put these two things together, what do you got? You've got that Z, right, is what? It's the sum I equals 1 to m, parentheses, the sum j equals 1 to n of A I j, beta j, alpha I. Right. So this definitely proves spanning, right? In the sense, well, spanning of what, right? Spanning of what? So this shows that Z is an element of the span over, let's see, the AIJs are where? They're in F. Span over F of the set alpha sub I, beta sub j, such that 1 less than or equal to I less than or equal to you fill in the blank, 1 less than or equal to j less than or equal to you fill in the blank, m, and I guess I filled in the blank, sorry. It just takes a long time for you guys to walk up here and write stuff, so let's move it along. So this is a potential basis, right, for L over F. At least it's a spanning set. Maybe we've already proved it's a basis because does this calculation show that these coefficients aij are unique for the element z? I mean, the C1 through Cm are unique. And for each one of these, the aij's are uniquely given. If you're worried, though, to be sure that it's a basis, you can easily prove that this set, alpha I beta j, is linearly independent. And it's probably instructive to do that. It's very reminiscent of the arguments we made about independent subspaces in linear. It's like trivial linear combinations all the way down. So you know, if we start with this sum over, let's see here. I gotta be careful how I arrange the sum. I mean, sum over I and j, so to speak, aij, alpha I, beta j. If I set that equal to 0, right, I can look at that as what? I can look at that as, curses, I gotta, takes me a second to figure out which one's the bigger one, which one's the inside one, you know? I lose track. Let's see, L. Alpha, right? So we can write this as, I mean, this is essentially the sum j equals 1 to n of a what? 1j, right? 1j beta j times alpha 1 plus parentheses sum j equals 1 to n a2j beta j parentheses alpha 2 plus plus sum j equals 1 to n alpha, how many a's do I have? How many alphas do I have? I've got m of them. A sub m j beta j alpha sub m. Now all that's equal to 0, right? And the things I wrote in parentheses, what are those? Yeah, this is element of where? I think those are elements of of k, right? But those are scalars, right? So we have k independence of the alpha basis, right? So by the k independence of the alpha basis, all of those numbers have to be 0, right? But the fact that each one of them is 0, then we use linear independence of the beta basis to then obtain that each set of coefficients, right, whether we're looking at I equals to 1, 2, or even m, those have to separately be 0 using the linear independence of you know, so this implies that the sum j equals 1 to n of a I j beta j is equal to 0 for all I equal to 1, 2, m, right, by the k linear independence of alpha basis, right? And then finally, then, I'm tired of writing this. Let me call it star. Okay, then star equals to 0 implies that aij equals to 0 by the f linear independence of the beta basis. All right. I just wanted to be careful for once in here. So that almost happened today. I took a slide on this yesterday. I almost bought it. Like I slid like a solid foot on this. I just hit it just right and kind of drifted. So any questions about this? I mean, it does not, okay, so here's the main, what the rest of the section is basically about is sometimes, oh, no, I'm still not there yet. This is the, this theorem is not about adjoining elements, right? It's just about extension fields. It gets more interesting when you take a base field and you adjoin two elements. It may or may not be that you have the strict equality. Like the inequality is kind of the interesting thing that's coming up. You know, silly example, if we take the rational numbers and we adjoin like the 4th root of 2, right? If we then adjoin square root of 2 to that, you know, it's still just q adjoining the 4th root of 2 because the square root of 2 is already in, you know, the extension by the 4th root of 2. But generically speaking, if you take two elements, one of degree m, one of degree n, algebraically speaking, two algebraic elements over a field, and you adjoin both of them, then the degree of the extension is the, you know, it's at most the product of their degrees. So if I take a degree 3 element and a degree 4 element, I adjoin both of them, I have at most a degree 12 extension over the base field for these two things. In fact, the culmination of the section says, in fact, that has to be degree 12 because 3 and 4 are relatively prime. That's the, you know, jumping to the end of the story. That's what we learn. Okay. Move it along here. Oh, and of course also the infinite case. Can you guys see why the calculations on the board? I mean, we don't have a basis in the infinite case, do we? But I suppose you can sort of argue by contradiction. You know, if you have one side finite and the other side infinite, I think you'd get a contradiction. I mean, he's got a paragraph here. I suppose I could read it. He says, if k over f is infinite, then there are infinitely many elements of k, and hence L, which are linearly independent over f, so L over f is also infinite. Similarly, if L over k is infinite, there are infinitely many elements of L linearly independent over k, so certainly linearly independent over f. So again, L over f is infinite. And of course, we've already proved that if both are finite, then both are finite. So in short, if any of the above, I think, are infinite, then both sides have to be infinite. Well, I guess not. It could be this is infinite, and one of these is infinite, but not the other, right? Yeah. Okay, so corollary. Corollary 15. Suppose L over f, right, is a finite extension. Excuse me. Finite extension, and K is any subfield of L, all right, containing f. Right. That is, f is a subset of K, which is a subset of L. So it's that condition again, right? Then, sorry, I wrote all that. I didn't need to read all that. I'm an idiot. I should have just said, by this, obviously, the degree of K over f divides. I mean, don't be distracted by the multitude of symbols I just drew on the board. All I'm saying is that if you have this is equal to the product of that and that, then apparently this divides that, right? So K over f divides L over F. Proof. This is immediate. Yeah, good job. All right. But, you know, the proof is not especially exciting. The application to examples, though, that's where you start to hit some pay dirt here, so to speak. So this is example 1. I will, again, talk through with you guys. So, of course, we have, if we say alpha has, well, alpha is real root of x cubed minus 3x minus 1, all right, equals to 0. And he says between 0 and 2. I think the point of saying that, all right, is that we don't want to solve for alpha. We're going to describe alpha using calculus. Right? We know, how do we know that a real root exists there? Well, that's calculus 1. It's the intermediate value theorem. You plug in 0, you got minus 1. You plug in 2, you've got 8 minus 6 minus 1, you got 1. So we're changing from negative to positive on this interval. By the intermediate value theorem, there exists such an alpha. So it's there. There is such a root. So the point of this example is that he's going to argue that alpha is not an element of Q adjoining the square root of 2. All right. So what's the, we can just argue by degree is the point, right? So if we look at Q adjoin alpha over Q, we have degree 3. We look at Q adjoin square root of 2 over Q, we have 2. He says 2 does not divide 3. So it follows that the square root of 2 cannot be written as a rational linear combination of 1 alpha and alpha squared. All right, keep me honest, guys, here. How am I using corollary 15 precisely? Which is the K, which is the L, which is the F? F is Q. I got that. Right? Pretty sure about that. What's the largest extension here is the adjoint alpha, right? So that's playing the role of L. And the point is that the K, which we're thinking of as Q adjoin square root of 2, that cannot play the role that's set forth in corollary 15, because if it did, it would imply that 2 divides 3.
Are you sure it should be the other way around? That K should be Q join alpha and L should be Q join square root of 2. Because if we're talking about alpha being in Q join the square root of 2, then if it went...
No, we're asking, no, the question, I bungled the statement. Your comment is correct, but born of a misstatement of the problem. The question is whether root 2 is inside Q adjoin alpha.
Oh, okay.
Thank you. Thank you. You are justifiably confused. As I share with you sometimes, I was almost held back because of dyslexia. I don't think I actually am dyslexic, but I do have a certain tendency to juxtapose ideas, annoyingly. why critical thinking is very important, especially for you guys. You should be critical. Thank you, Sam. Now, does it make sense? So, to say that, of course, K can't be a subfield of L here. I mean, Q adjoin root 2 can't be a subfield of Q adjoin alpha. That would apply 3 divides, exactly. I think it was 8, no, 2 divides 3.
Oh.
It's the
Yeah.
it's the intermediate. It's the degree of the intermediate field over the
Right. Okay. Yeah.
the most awesome field. I mean, we need what's the top field? The top field. I mean, these tower of fields. We usually, I know we call the one in the middle the intermediate field, right? In this situation, this is the intermediate field. This is definitely called the base. And I think I would usually, in a discussion like this, I would tend to call this the top field, just so we have a language. But to say that, you notice though that saying that K is not a subfield of L here, that Q adjoin square root of 2 is not a subfield of Q adjoin alpha, that implies at the level of elements, right, that the square root of 2 is not in Q adjoin alpha. Because if it was, then by closure of the field, you get everything else. Right? And move along here. So his next example oh, probably should have erased that. He says, look at the 6th root of 2, right? And, join that. 2q, right? Then, of course, this has minimal polynomial what? Just x to the 6th minus 2, right? That's the polynomial of minimal degree, which takes the 6th root of 2 as a 0. It's irreducible by Eisenstein, so good to go. In particular, we have that Q adjoin the 6th root of 2 is a degree 6 extension over Q, right? And so he points out that the 6th root of 2 cubed is what? Right. And so what's that show? That shows that the square root of 2 is an element of Q adjoin the 6th root of 2. So that implies, of course, that Q adjoin the square root of 2 is a subfield of Q adjoin the 6th root of 2, right? And so we can look at the diagram again. We got our Q, right? And over that, I don't really need arrow. Q, and then we've got Q adjoin square root of 2. Then we've got, so I'm drawing my field. We usually draw these diagrams vertically. It occurs to me that I'm just being, I just fell victim to Dummett and Foote's typesetting. I mean, it does have 900 pages. They're not that careful with their spacing, but of course we know this is a degree 2 extension, right? We know that this altogether is a degree 6 extension, right? So what does that say? By the corollary. That has to be 3, right? Which incidentally tells you, what does this tell you? This tells you that the square root of 2 in Q adjoin, well, sorry, Q square root of 2, how to say this? No, wrong way to say that. What I'm trying to say is the 6th root of 2 is degree what over Q adjoin square root of 2. Right. Now here, again, we're using what we did last time, which was that the what's that?
X minus square root of 2. I mean, you've got x squared minus 2 is the minimal of square root of 2 over q, but the linear one is the minimal over r.
I'm not following yet. I'm sorry. I'm not saying what you're saying is wrong. I just don't. I didn't follow yet. I mean, I guess you could ask, what actually is the minimal polynomial? What is m? The this element, right? 6 root of 2 over q adjoin the square root of 2 of x. X cubed, right? Apparently. And then plus something and something else. I don't know what those things are.
I think it's just x cubed
Minus radical 2? Let me see here. Cool. Very good. He says, showing that this polynomial. Oh, I know what. I was thinking that's not complicated. What you just did. I mean, that no offense, but I should have seen that. Shame on me. What's complicated is proving that this is in fact an irreducible polynomial over that field, over Q adjoin root 2. But remember, last time we proved that the minimal polynomial is irreducible. Right? I mean, the fact that this theorem gives us that this is degree 3 over that field says that the degree, if you can find a degree 3 polynomial which is monic and takes it as a 0, it is the minimal polynomial, and hence it is irreducible. So we get irreducibility just from dimensions, as opposed to much more heinous calculations. So that's neat. All right, so I feel like we already had this definition, but here it is again. I must be missing something. Oh, I know what it is. An extension, I missed the very important word finitely generated. I was like, we talked about extensions with adjoining elements before, but we had not insisted that it's finitely generated, right? And all that means, that's basically just putting a limit on the extent of our list, right? And then, so this notation still means the intersection of what? All subfields of K, which contain what? Both F and the elements alpha 1 through K, right? It has to be closed under the operations of a field. They have multiplication, inverses, sums, all that good stuff. Now, so lemma 16. We have that F adjoin alpha beta is F adjoin alpha adjoin beta. So if we think about this, I mean, the proof is essentially just by minimality So, this is much like if we talk about polynomials in two indeterminates. It's almost the same kind of thing, like similar to the idea, right? I feel like conceptually this is much akin to this thing. If we take polynomials in two variables, right, you can look at that as polynomials in the first variable giving coefficients to polynomials in the second variable. I mean, it's kind of the same idea, but it's not the same idea. It's just a similar idea. I mean, this kind of tells you how to do this calculationally. We kind of already saw it in the proof of the theorem I just erased. The alpha basis and then the beta basis, and we multiply the two, and I mean it's almost the same structure. Of course, this is the smallest subfield of K, which contains F, alpha, and beta, right? But this field does what? It definitely contains beta, and it definitely contains what? Anything in F alpha, because of the constant polynomials. I mean, because this field is also in the extension by beta. So it's got F, but then it's got F and it's got alpha. So this one's got F alpha and beta. This one's got F alpha and beta. By minimality, they must be the same. Yeah, it's almost silly. And if you can do it for 2, you can do it for K, is the next thing he says. All right, and getting to the point here, Theorem 17. The extension K over F is finite, right? If and only if what? K is generated by a finite number of algebraic elements over F. The gory details, of course, are written out in Dummett and Foote, but I can kind of explain the basic idea just with words. The point is, if you have a finite extension, right, that means that you're adjoining K elements, right? But you can look at that as being the field with K minus 1 elements adjoined with the kth element, right? And because that's a finite extension, it follows that the alpha sub K is algebraic over the F with the K minus 1 elements adjoined. And then you just repeat this argument. So if we look at F with the K minus 1 elements adjoined, you can look at that as an extension of the K minus 2 elements with the K minus 1th element, which proves that that K minus 1th element is algebraic over the K minus 2, all K up to K minus 2 elements, right? And you just keep doing this. And eventually you get to prove that even the kth element is also algebraic over the base field. Everything's algebraic over the base field. It's just combining the fact that every finite extension, right, that every finite extension is an algebraic extension, and this relation and the extended version of it basically says that the finite extension of finite extensions is still finite. Yeah. So I'm not sure I've done that justice, but it is definitely done justice on page 526 of your book, so I'll let you look at that. Now, corollary. I suppose I could give up on doing module theory in here and actually prove all these things, but I think it's healthier for you guys to see a little less proofs on this stuff, and because I think in the process of doing homework, you guys will get closer to understanding whatever I have, glossed over in here. It will become real to you in the homework. Yeah, this is true. As I told you, my temptation is always to try to recreate Dummett and Foote, and I find it to be suffocating because so much detail. All right. anyway, long story short, corollary 18 is kind of important. If we have alpha and beta algebraic over f, all right, then alpha plus or minus beta, alpha beta, and alpha over beta, for beta not equal to 0, of course, are all algebraic. And corollary 19 says that if we have L over F, a arbitrary extension, then the collection of elements of L that are algebraic over F are what? Form a subfield of K. Try to absorb what I'm saying here. So for like the most important, probably the most important example of this is if we say look at complex numbers, right? Over, I don't know, over the rationals, right? Then this says that the collection, oh, everything's algebraic. I chose poorly. I think Q has got to be at the top, right? No, how would I say this? Dang it. Oh, reals.
Wait, where does it take to corollary 19?
Yeah. What did I do there? That seems suspect, doesn't it? Corollary, what was I? Oh, they form a subfield K of L. That makes more sense. Thank you. So I guess we could look at the rationals, right? And we could call this thing K, right? And I keep drawing my field towers. They'll fall down. It's no good. So let's say the reals of the top field. This field given to us by this corollary is K, and Q is down here, the base field. There we go. Right. So that would be all the algebraic numbers over the rationals.
But aren't the set of algebraic numbers, or do you by algebraic numbers, you not just mean like the conventional meaning of like the subset of the, there are some algebraic numbers over Q that are not real, right?
Well, these would be, oh, okay, so yeah, you're right. These would be the real algebraic. This would be the real algebraic numbers. Okay, right, so if I put C up here, then we get, right. I'm sorry, I'm getting the second part of the example mixed up with the first part. Sorry about that. And this is called, I believe this is called what? This is called Q bar. Is it called Q bar in his book?
Yeah.
I think it's the algebraic closure of the rationals. See, using the topology idea of closure, kind of. But that includes like square root of 2, square root of 3, square root of 7, the nth root of 2, right? For arbitrary n, so that's an infinite. It's infinite over the rationals. But it's still, but this, so every single number you can construct by a polynomial equation is in here. Every last one of them. The fact that it forms a field is given by corollary 18. See, because if you take two algebraic numbers, you can construct their sum, difference, and reciprocal as needed to form a field. right? But I think what's really interesting about this is, it seems so huge, right? All possible algebraic numbers. And yet, he carefully argues that this is countable. It's still just as big as the natural numbers. To me, it's already fascinating that the rational numbers have the same cardinality as the natural numbers. That, to me, is weird. I mean, that is weird, right? It's just weird, but it's true. And this thing seems fantastically larger than the rationals, but it's in terms of cardinality, no, it's still that same size.
Even the computable numbers are countable.
Oh my goodness, computable numbers. Phew, yeah. Anyway, that's about it for this section. Like I said, he ends with just looking at ends at looking at the composite of two fields. So if we take a subfield K1, a subfield K2, their product K1, K2 is defined to be the largest. It's basically the intersection of those two subfields inside the larger field. And he uses what we've done so far to argue that the degree of the composite is at most the product of the degrees of the subfields composed. And at the final end of the section, if they're relatively prime, then it's equal to the product of their degrees. So anyway, and then the next section, of course, is on constructible numbers, but I'm out of time. So, I mean, I can summarize it. All of the classical compass constructions imply that we're adjoining degree 2 algebraic number to the rationals. And if you could square a circle or trisect an angle implies the existence of a degree 3 extension over the rationals. And squaring the circle implies the existence of a transcendent element. It's basically the construction of pi over the rationals, neither of which are possible with straight edge compass constructions because those are degree 2 extensions. In fact, that's all I was going to say. So I guess I said it. Haha. To splitting fields. But by the way, that section, if you